questions about the homework? Anything? People in chat? People in,
I know this has been asked before, but is it still due Friday?
Yeah, in May,
Sure. Yeah, I mean, I'll publish homework 2 before, so of course it's a good way to build lots of tasks for the deadline, but yeah. But sure, Monday will be fine. But Monday I might want to speak about it, so Monday will be a firm deadline. And I want to remind you the rules about what is cheating versus what is a good collaboration, meeting without papers next to a whiteboard or so, chatting about the homework with small teammates, perfectly fine. Discussing things that you have some idea how to solve something, go meet your colleague, maybe have a verbal discussion, and then go home and write down what you got. That's perfectly fine. Submitting in pairs also perfectly fine for this homework. We will have, of course, separate homework, but I wanted to get you into started to the submitting in this one in pairs is also fine. Not more than pairs. What is definitely not fine is to find something on the web and cut and paste it into my answers. That's needless to say. It's amazingly easy to see answers that looks like they are relevant, but they are actually answering slightly different question that just cries out, I have no clue what I actually wrote, but it seems relevant. Or somebody told me that that's the right answer, but I didn't even understand the question well enough to verify that it's even the relevant answer. Yeah?
On that vein, if we were to look into an algorithm that we found on the internet, but actually understand it and explain that algorithm, is that okay, or does it need to be entirely written itself?
If it's in the level of you got the right idea and then you wrote the algorithm yourself, it's fine. I mean, it's really a gray area. Practically, of course. Sure, but so the short answer, if it was intellectual property of somebody else, but you understood and got the idea and articulate it well in your words, it's fine. But it's a very bad recipe for the midterm, needless to say. Because in the midterm I'll ask, when I'm grading questions, if I'm asking a question that is similar but different, similar and different than the question that I ask in the homework, and people are answer wrongly, and I expect everybody that thought enough about this question should be able to answer. Sorry. Question 1 belongs to the homework. And then question 2, that is almost question 1, is in the midterm. And these two questions are very similar. So I expect everybody that thought hard enough about question 1 to be able to answer question 2. And then you don't, then I'll grade it more harshly than had question 2 appears completely separately and it's just a hard question, right? It somehow tells me you didn't really understand your answer from the homework. So either because you had a fantastic partner in your homework that did all the partnering. Oh, you cannot hear me. Okay. Sorry, people tells me that they cannot hear me. This is my fault. Can you hear me now? Zoom people? Okay. Thanks. Thanks for letting me know. about textbook, I wanted to show you something interesting that actually I didn't know about. So this is a website of one friend, colleague of mine, Israel Pellet, that is actually very smart and wrote a really good book about geometric algorithms. Now, as you know, there is ongoing argument in the last years between publishers and scientists. It says cost of knowledge is too high, you're paying too much for books and many journals, and publishers saying, yes, but we like money, so we will keep charging a lot of money. So Sariel wrote a really nice book, and published it, and of course he has a contract that he's not going to put it online. So he doesn't put it online, obviously, and he said that you cannot approach the online version. And here is how you are not approaching the online version of the book. I'll read to you. Sorry. So yeah. So as I said, since you are not allowed, since I cannot publish an online version of the book, here is what not to do in order not to get his book online. Okay. And if you'll fail to do it, if you'll fail not to do it, then you might find the version online. And in the same link, you'll find various books, a lot of books that are fine and legal to download, including the data structure book of Annenberg and Lewis, which is a book about data structures, the Splay Trees that we'll discuss today, and the skip list that we might discuss later appears very nicely in this book. But a lot of other books also. Yeah. Okay. Homework question, we covered it up, unless you thought about something. Yeah. Let's talk. Recording, by the way. So I want to talk about Splay Trees, which is an excellent example where we are really needing amortized analysis. This, for example, this accounting method that we talked about giving dollars to items in your data structure, and every time that you are performing something, then items in the data structure, or you yourself will pay for it, but you're paying it via you'll give it to element of the data structure, and the data structure will be charged every time that an item is accessed. So we mentioned this method in two relatively easy examples, the binary counter, well, also the stack if you wish, and we talked about expansion and contraction and shrinking of an array where it was already an example where you really needed to put dollars on the items itself to make the analysis when we started to talk about deletions as well as insertions. I want to move to a good example where amortized analysis is really needed. What I'm not discussing here is something called the potential function, like the energy function of data structure, which is another method to do amortized analysis that is similar, and you'll see today where it's tangent to what we are doing, but it's not exactly this part. It's a bit more formal. I want to talk about splay trees. So splay trees are binary search trees, not necessarily balanced. Balanced will mean the height is order log n. Here we are letting this constant go, this notation go. The height of a splay tree might be larger than log n. It might be all the way up to n. Okay, so and in a splay tree I can do a lot of operations like any other search tree. Search tree, you know, you have the root, everything to the left is smaller or equal, everything to the right is larger than. We can do find as normal. We can do insert, obviously. We can do delete. So far, by the way, hash table will do these operations for you, but you need a few more. You can do merge of two different trees, provided that every element of one tree is smaller than every element of the other tree. We'll only merge elements only if everybody here is smaller than everybody here, then we can merge the two trees. We will split two trees based on value x. Everybody here in one tree will be smaller, everybody in the other tree will be larger. There are algorithms that need these operations directly. We will use these operations also to do the insert, delete, and delete we will do via the split and via the split and merge operations. Okay, and the main operations of the splay tree would be splay of an element x. I'll pick an element x. It might be a key or it might be a node that is not the key directly. It might be the successor, the element that comes immediately after x, or the predecessor, that element that comes immediately before x, if I look at all the elements in the tree sorted. That would be the splay. I'll pick on some node, and then I'll do a sequence of rotation. Like I'll make sure that the tree is a decent search tree as I'm doing these rotations. And at the end, this node that I picked on x will be at root. Okay, how many of you have heard about splay tree? Worked with splay tree? 1, 2, 3, half the class roughly. Okay, so
So what will be the final result of splitting the tree, that the x moves to the root?
yes. It's not the purpose, it will be a tool of it. What we want is to do find, insert, delete. And as we'll talk about augmented data structure, like keeping some weight on each node, telling me how many people have salary between something and something, or how many nodes are in some range, or what's the total salaries, total weight of people, what's the average of some range. That we need some order into it. We'll talk about it when we'll talk about skip list. About it. When are we going to have the meetup, guys? Do you want to pick a Monday or Wednesday? maybe Wednesday, so we'll have more time for review. Otherwise, we have to have a review at the weekend. I don't care. Maybe it's a later part of October or the beginning of November, somewhere like this. What's a date that will work best for you in terms of other midterm deadline? That is, to avoid other deadlines. Somebody wants to make a suggestion now, or we'll wait with this for next week?
Maybe we could do a poll on Piazza.
Okay. Poll on Piazza, we'll do. And obviously, if you have some really justified reasons, you can do it. Talk to me. Why some day doesn't work for you. I already know about people that go to conferences, already health issues, etc. Talk to me and we'll find a solution. So, just to make a rotation, in this tree, let's say that I want to splay 19. Splay 19 actually, by the typo, splay 19 is already at the root. So what happens if I do splay 17? This will take just one rotation, right rotation, at which I pick these two nodes, and I want to push 17 to the root. Remember, if I just replace these two keys, but leave the node as is, the tree is likely to stop being a search tree. If I just switch 17 and 19. Instead, I'm doing rotations that always keep it as a search tree, meaning I'll push 17 up into the root. 19 will move down. That's the simplest rotation. 13 will be the other child. And next, we have for subtrees alpha, beta, gamma, delta. And you check that if I'll put them in the only possible way, alpha, beta, gamma, and delta, this is the only way to arrange these subtrees, it is still a good search tree. Okay, but it looks strange because why this looks strange? Because I might have, we all know that, or we all were trying to think that you cannot do better than a perfectly balanced search tree. Perfectly balanced will mean the height is not only order of log n. The height is what's the best I can hope for, log to the base 2 of n, think y plus minus 1. And you cannot, and that's just the same as binary search in an array. Like AVL, red, black, etc., they all give you worse constant. While my splay might have start from a very nice, well-balanced search tree and destroyed it. And yeah, that's fine. So I might destroy something to the tree. Still, why do we like Splay tree? Why it's a big highlight about them is that I don't need to store any information in the tree. AVL tree need to store the height or something like this. Splay tree, not. Save a bit memory, but that's not a big deal. Sequence of a lot of operations will be as good as a search tree. One operation might be costly, but if I'm doing a lot of operation, I will do, if I'm doing M operations, we'll take M log n. And here is a size, how many keys I have in the splay tree. Okay, which is also, so far it's not, you can say, use AVL, use red, black, and you'll do the same. because the height of the tree is always log n, as opposed to the splay tree. Right, it will be, if you have a tree with height log n, then each operation takes log n insert delete fine. Where the splay trees are really useful are when some nodes or some keys are accessed more frequently than others. If the 17 that is here, I'm going to access it many times, like 90% of the find operations that I'm doing are find 17, then I want 17 to be very close to the root, because now I can beat the log n per operation. If it's in the root, it's to find it, it's just constant time. Okay, so that's where this, and if I know what is the frequency of operation, which keys are frequent, which keys are not, then I can design an optimal tree for it. But I have no idea what the future is. You know, it's very hard to predict, especially the future. I don't know which keys are going to be popular and which are not. But the splay tree will be fine with it. It will arrange itself so that if you're doing enough many operations, nodes that are very popular will be very close to the root. Nodes that are very unpopular will be far away from the root. If you want me to go more into it, it's actually getting into the entropy of how do I get into accessing these nodes. Exactly. If in case that some nodes are very frequent, some are very infrequent. Okay, and I'm happy to go more beyond it. It starts to touch into information theory. But not today, just to show you how do I do rotation in splay trees. If you know AVL or red-black, it's the same type of rotation. We have 3 types of rotation. Here is a node X, and X has a single parent but doesn't have a grandparent. That's the case that I showed right here. I'm moving X up, moving P, the parents of X, down. And now these 3 subtrees, maybe you don't see their letters, but there is only one way to arrange them. Right? I have now a lot of several pointers that are unoccupied. I'll arrange these pointers according, so they point to these subtrees in the same order, from left to right. That was one type of rotation. That was a right rotation. Of course, if I want to access P, then it would be just the same rotation, just in the opposite direction. That if P doesn't have a grandparent, that is, if X doesn't have a grandparent, that is, it's already next to the root. More commonly, X does have a parent and a grandparent. And in this case, we have basically 4 types of rotations. But our symmetry, it can be zag-zag or zig-zig or zigzag operation, if you wish, which says here is X, and X is a left child of a left child of the grandparent. So I'll take these 3 guys, and I'll rearrange them just by doing 2 right operations, rearrange them in the only possible ways. Again, X wants to be as high as possible. And in this case, by the way, it's definitely possible that the grandparent has a parent of its own, and we need to continue. That would be the common case. The grandparent has some more nodes, but X is now replacing rule with the grandparent. So X is closer. The distance from the root to X was decreased by 2 by this type of rotation. Of course, if now I want to access a grandparent, I'm just going in the opposite direction. Now, if I have a zigzag operation. X is a right child of a left child, or is a left child of a right child, symmetric. Take these three guys, rearrange them in a tiny, small balanced tree, parent X and the grandparents, and now the subtrees of these trees are just arranged again from left to right. So either case, X is closer to the root, and then I'll continue pushing it to the root. Everybody understand what's going on here? And again, when I'm doing it, I don't check anything. As opposed to AVL, I don't store any extra information in X. I have no clue about how balanced or imbalanced the tree is. Okay, and now we want to say, did I just lost the slide? Oh, wait. How come we skip this slide? I might have switched over. Okay, now every other operation we are doing via the Splay operation. Meaning, insert of X. Insert of X, you know how to insert a node into a search tree, which is just make it into a leaf, right? I want to insert a 3,000, very large number. I'm going all the way, making 3,000 into a leaf, voila. And basically doing find of X. I didn't find X, so I'm inserting it as a leaf in the place that it should be. And now I'm performing Splay of X after that. Merge of two subtrees. Remember, we are merging two trees only if every element of S is smaller than every element of S prime.
So whole of the tree has to be smaller than the S dash?
Yes. So how do I do it? I'll pick the largest element in S. Oh, well, pretend that I'm doing find of this largest element, look at who is the largest element, and pick the maximum and do Splay of this element. It will be the same effect as if you're doing find of infinity. You'll end up your search in the same element. So if our tree (17, 3, and 19). I'm finding the largest element, which is 19, doing one left rotation. So I'm ending up with 19 and 19, 17, and 3. Why 19? Because it's the largest element. And now I know that not only that that I picked the largest element of S, now this largest element in S is in the root, and obviously it doesn't have any right subtree because it's the largest one. Nobody is larger than it. Meaning that now I can take the other tree, S prime, and connect it as a right child of this new element. That's how I'm doing the merge.
What happens if a few elements are equal in the other tree? Equal to the original tree?
I'll assume that it's strictly smaller than. You're right. So I need to break. I need to use to break ties somehow. So the assumption is really everybody is smaller than. But there are algorithms that need these operations directly. We'll describe it to see how we are performing a now delete operation. Deletes in other search tree will want to say, I want to delete somebody, so I'll make this 19 a leaf, and leaves here are easy to get rid of. They don't destroy the tree. Right, we are replacing 19 with like the smallest element in its white subtree, and then it's fine to replace places. Splay said something else. Splay said, no. If it's close to the root already, let's take advantage that X is close to the root. I don't want to push it down the whole tree. It's very expensive. The tree might be quite high. Instead, if it's close to the root or not, I will, to do the delete, I will first move X to the root and get rid of it. Getting rid of it will mean that now I have two separate trees. One tree is all smaller than X, smaller or equal than X. One tree is strictly larger than X. And now I can merge them just in this way. Make sense? Get rid of it and do splay and merge. OK. So that's how we are doing delete and various other operations. We talked about the rotations. And let's talk about what the running time of a sequence of a lot of operations. So just to make sure, if our tree looks like this, a long path, it's absolutely fine, even though its height is n. And if I need to find the lowermost element, I need to spend n time out of it. What I want to argue is that maybe the first time that I'm accessing 30 over here, maybe the first time that I'm accessing 30 will take a lot of time, but after that 30 will be closer to the root, so, and the whole tree will be more balanced. So let's start to make it formal. Each element, once it's involved in a rotation, needs to pay for its rotation. So each element needs to keep some credit. If you are involved in an operation, in particular rotation, the element X needs to pay for the rotation. It needs to have money. Same way that in the dynamic arrays, every time that somebody was copied from one place to another, this had to pay for it. Same goes here. So how can I arrange the money? I'll put on every node some amount of money to start with. And in addition, every time that I'm performing an operation, I'll have to invest some more money. But as we'll see, no more than log n, many dollars per operation. And this money is fluid. Some nodes will give it to other nodes when needed. So how do we arrange it? So for every node x, n sub x is how many nodes there are, including x itself, in x subtree. N sub x, is the font good enough, guys? And it's readable. N sub x, 17 will say that n sub 17 right now is, well, 3 nodes in 17th subtree. And 3 will say n of 3 equals 1. And I'll tell you what's the rank of a node. The rank of x is log of how many descendants, including itself, it has. The rank of x, R of x, is a log of n of x. making it a bit larger in OBS. So what's the maximum value of the rank of a node? The root, you have n descendants, so it's log n, log to the base 2 of n, to be precise. Okay. If you're a leaf, then it's log of 1. You don't have any children. And we will have the credit invariant out there, which would mean that every node always have its rank many dollars. Even though this node has to pay for operations, every time that this node has to pay for a rotation, it gives the rotation $1. So even though the node has to pay with it, this invariant will be satisfied after every sequence of operations. Now, when I decide to perform an operation, even in a tree that look horrendous like this, I will have, if I'm going to search for 30, I'm going to spend some money to add money to the system, because the 30 has to pay for rotation, so I'll have to pay some money, but the cool thing will be I don't have to pay more than log n. Even though I'm doing more than n operations, here 30 is here, I'm doing to move 30 all the way to the root, I have to do about n rotations. Nevertheless, the amount of dollars that I have to add to the nodes around it will only be log n. But we'll have to argue why, and it's going to be quite cool. Okay, so what will, if you'll believe me about it, and you're saying, how many rotations did I do for a sequence of m operations since we kept the invariant? Every rotation was paid by, eventually me, but by the node that was involved in the rotation. Then if it only cost me m log n dollars to give to the system, and the system didn't use more than m log n and still paid for all the rotations, conclusion, the overall time was order of m log n. And the number of nodes, once again, m operations of any type. Insert, delete, splay, find, etc., merge, m operations, and keys. All in all, it takes m log n. And as I said, it takes less if the entropy is larger, if some nodes are more accessible than others. But let's prove the m log n. So, credit invariant, each node x always has Rx dollars, credit of Rx. And our investment lemma will say that each splay operation requires me as a user, as the one that called this operation, even in the case of the extreme tree like this, will ask me to add only log n many dollars to the system. To be precise, that's the amount of dollars that I have to add. It's the end. But some node will pass, nodes needs to pay for the rotation. 30 needs to pay for a lot of rotations here and rotations. And how will it pay for it? It will take some money from other nodes. But we'll see that it can be rearranged. And I'll add to it this amount of money, the log n many dollars. Okay. The cost of a single step of the splay tree So a single step of the splay tree, it involves x, its parent, and maybe its grandparent. At most 3 nodes. And we will think about R of x, the rank of x before the rotation, and R prime of x, the rank of x after the rotation, where it's closer to the root. Now, not too surprising, but when I'm moving from here to here, looking at the R of 17, the rank of 17, when is this larger, before the rotation or after the rotation? It is larger after the rotation because now it has only alpha and beta as subtrees. R of x is log how many children it has. If you have more descendants, then your log of this number is larger. Right? So you have your rank increases the more descendants you have. Children, grandchildren, grandchildren, etc. Here, how many, where was its children? Only what you have in the subtrees alpha and beta. Here, what do I have as a descendant of 17? Alpha, beta, and in addition, gamma, delta, 13, and 19. More nodes, so your rank is becoming larger the higher you go. Now, on the other hand, the rank of 19, of course, go down. It has fewer nodes after the rotation. So, the cost of a single step of the R tree, it involved 3 nodes. It is, because we are doing either 1 rotation of 2 rotations, like a zigzag rotation is like rotating right and then rotating left. And assume that the credit invariant, each node has log n many dollars in their bank account, was true before the rotation, and R prime would be the rank of x, the one that goes up, after this 1 or 2 rotations, 1 step of the splay operation. Splay of 30 requires a lot of rotations, but after each such step, here we start by rotating these 3 elements, putting 30 over here, and then arranging these 3 elements, putting 30 over here. After each such step, the money invariant is true. But here is a lemma without a proof that I'm not sure that there is, after x pays for its rotation, the system has much money. So I have to add a bit more money to the system. How much money do I need to add? I look at the rank of x after this 1 or 2 operations, minus the rank of x before the rotations, and I'll pay at most 3 times this number. Which by itself doesn't tell me much. It means that I need to add maybe a constant per rotation, and I'm doing a lot of rotations. So maybe it's a lot. And if I'm doing n operations, then this lemma by itself doesn't save me much. This value, the difference of my rank before, difference of the rank of 17 before and after, might be different by constant. You're doing n rotations, then it will cost you n constants. So that by itself is not saving me. But it tells me, but where does it help me? Note that the rank is the floor of the log n, so it could be 0 sometimes. And even if it's not 0, I'm still not in troubles. Because let's think about a sequence of rotations. We are doing something that is very common in amortized analysis. Using this lemma, using this lemma without a proof, using this lemma without a proof that each rotation takes this many, let's prove lemma 1 that will tell us that overall for the whole process, I need to add only log n many dollars. Why is this? Let's write by, let's see if I can increase this font. I didn't expect it to be. The projector adds this extra layer of fuzziness. So might be too hard in real time. So let's at least make it in full screen. But now the OBS doesn't catch it. OK, I think that it's probably good enough. So R of k will be the rank of x, but after the kth rotation. I have k steps pushing 30 up. First rotation, second rotation, third rotation, each time I'm doing this rearrangement. R of k would be the rank of after the case operation. So don't get lost. We are talking about one splay operation, one splay of 30, pushing 30 all the way up. But on its way, there is one rotation that moves 30 to here and another rotation that moves 30 all the way to the root. Maybe more rotation. So I'll enumerate it as the first rotation, when 30 just barely moved up. The second rotation, k here in the parentheses, will be 2, maybe 3, 4, 5, all the way up to k. And after k step, then where is x? X becomes a root after k steps, k rotations. So the rank of the root is log n. Didn't prove much, but at least after the kth rotation, the rank of the root was log n. And notice that k before that had some amount of money. We had the money invariant. You are storing log n money with you to start with. Now let's use this lemma and let's ask, how do I pay altogether? So at step 1, I paid 3 times R1 of x minus R of x before. R1 is after one step, the new rank. 30 moved up to here, one step. I need to pay, but I don't pay yet. The difference of the rank of x, which is 3 times the rank of x after the one rotation, minus the rank of x before this single rotation. And then I'm moving to the next step, making 30 that used to be here. 30 that used to be here. I'm pushing it 2 more steps to the rotation. How much now do I have to pay? The rank of x, when it's here, minus the rank of x when it was here. Its rank increased. I need to pay it once again. If I have more nodes, then I'll have to do another layer of rotation. And at each time, I'm paying the difference of the ranks of x times 3. And here the magic happens. Because I'm not paying immediately right now. I'm waiting to pay at the end of the process. Let's look at this summation. R1 minus R0, R2 minus R1, R3 minus R2, R4 minus R3. It's called telescopic sum. Why? Because you are looking at the first and you see the last elements out there. Telescopic sum because this R1 of x appeared once here and appeared negatively once here. R2 appeared positively here and negatively here. R3 positively, negatively, they all canceled itself after a rotation. What am I left with? I'm left with the first element, the Rk, and the RK after K operation, it's in the root. In the root, its rank is log n. When I started, its rank was whatever it was, but I had enough money, log n, that was the invariant before I started, and everything else was canceled. So by delaying my payment until the end, all I need to pay is this 3 times log n minus the original Rx, which is less than 3 times log n. Voila. Sorry, the font is, I didn't expect it to be fuzzy. Okay? Altogether, sequence of operation, because of the amortized analysis, takes log n. So it's a bit surprising, right? One operation, one splay, I spend a lot of time, but I somehow improved the status of the tree. Like the tree has altogether, count how much money the tree has altogether, it will be n log n, right? Counting the money for everything. And every set of operation, including if the tree is very strange, still n log n. Do a very expensive sequence of operations, it could be. You need to work much more than the amount of money that you invested altogether, but you cannot do a lot of very bad operations. Your next play, the tree will be better. Your next play, your tree will be better. By doing this sequence of operations, the tree is becoming more and more balanced, even though a single operation might look like it breaks the balance. Kind of a magic. Cool. So that was a non-trivial example of amortized analysis. And the only part here that you didn't understand was a bit technical, a bit case analysis, that if I'm doing, let's say, this rotation, or if I'm doing any one of the rotations, then I take some of the money from here to here without a beta. If I'm moving from here to here, then, 17 has more money than 3 and 1. Their rank is only log of 1, making it 0. Their rank is 3. It's a bit larger. However, I'll shift money in between so that this lemma, this lemma that I'm investing at most 3 of the ranks difference will be correct. And that's just a case analysis. OK, we are done with amortized analysis. Let's start with a new topic. So we have 2 options that I had in mind. One is skip list. Don't know how many of you have seen it, how many of you really get into it. Other topic is when I helped people at office hours, I used a really cool, as an example, a really cool algorithm for finding the closest pair, which is similar to the probabilistic thing that you did in homework 1 and before in the quicksort, but it's a bit more clever. So, and we can do quicksort after that, but that maybe it will give you some ideas about homework 1. So maybe we'll do this part. But it's not the 3 weeks alert that I'm supposed to give you before that. But if it's OK with you, let's do it. Sure. That's going good. The OBS suddenly give me hard time. Okay, finally. No. I'm trying to fix the OBS. Okay, so a little cute problem with various applications in clustering, other algorithms that are similar. People, linear programming use the same. It's based on a paper by Matthias and Kuller. It appeared a while ago. So, definition. What am I trying to do? I have an input, and this input is a set of points. In this example, they are all living on the plane. And I want to find a good cluster of these points. To be precise, I want to ask, what are the 2 points that are the closest to each other? Who are the 2 points that are the closest to each other? Maybe it's P1 and P2 in this example. I measure the distance between each pair and check what the distance, and all I need to report is who is the closest pair. So, of course, straightforward approach, take the distance between every pair. Yeah. Order n square trivially. Can I do, if I'll give you n numbers, and I want you to do which are equal to each other, a problem called the element uniqueness. I give you numbers, k1, k2, k3, kn, just number, and I want you to tell me, are there any ki and j such that ki equals kj? That's a problem called the element uniqueness. Give me an algorithm to do it, please. They're just numbers, no points. Okay, how would you do it? As efficient as possible. Yes? Sort them. And log n. If they are unique, they need to appear one next to each other. There is yeah. Hash table will do better, but it assumes that the keys are somehow well behaved. And it's not worst case running time, it can be more. It's expected linear. And it's, wow, well, first great example that with randomized algorithm we can do much better than deterministic algorithm. There is a theorem that says that sorting was just one way to solve it, maybe there are other ways. That doesn't matter. It still takes at least omega of n log n time to answer. There is a theorem. There is a theorem that says at least omega n log n comparisons, just like matching. Matching takes at least n log n because you have to compare at least n log n many pairs. Same here. Same for element uniqueness. which implies that for my problem over here of the two closest points, I cannot have a deterministic algorithm that doesn't toss coins, that doesn't have randomness, that will do anything better than n log n. Right? Because if I'll put all my points, all my keys on a line and ask what's the distance between the closest pair if there is element uniqueness. If you have two equal elements, they need to appear at the same place. You can use this algorithm to solve the element uniqueness. And we said element uniqueness, based on this theorem, needs at least n log n. But randomized algorithm, you can beat it, because you can have an algorithm, where I'm going to tell you, an algorithm with expected linear time, better than the n log n. Okay, and how is my algorithm going to work? I'm going to keep a few data structures. First, I look at the points P1, P2, all the way up to Pn. And now I'll define Si. Si is a set of points P1, P2, P3, P4, all the way up to Pi, for every I. Si is just the first I points of the set S. And I'll keep the distance, D, the distance of the closest pair of each one of the sets. So that's called incremental algorithm. I'm adding the points one by one. Now, what do I know? When I move from S2 to S3, that is, what did I do? I started from the distance for S2. D of S2, the distance of the closest pair of S2. S2 contains this point and this point only. D is exactly the distance between them, no choices. And then I'm moving to S3. S3 might be far away from all this set. So this D of S3, the distance of the closest pair of S3, what happens to it? It will definitely not go up, because I already have, right? S2 Si is always a subset of Si plus 1. I added 1 point. So D will either stay the same or go down. If I put P3 just next to P2, then the distance will go down. If I put P3 just next to P1, the distance will also go down. In this example, the distance doesn't go down. But then when I'm moving to S4, that includes P1, P2, P3, P4, this distance definitely decreases. So the distance of S2 is larger or equal than the distance of S3. Could be the same or can go down, which is in terms larger or equal than all the way up to D of Sn. That includes all my data points. Make sense? Adding a point either keeps the distance the same or push it down. And now I'm putting a grid. Gamma, capital Gamma. I had an instructor that called it a hangman. Gamma of Si, what is it? It's a grid. You think about the whole infinite plane with infinitely many points in it. And I divide it into a grid using horizontal and vertical line. And by doing so, I create cells of the grid. I create cells of the grid. Now, I'll make sure that the grid size have one point at 0, 0. I mean, there is some coordinate system. There is some place. How did I tell you about this point? I gave you the xi, yi for each one of the points. So there is some point, 0, 0 in the plane, not a data point. There is 0, 0. I'll assume that the grid starts at a corner. And what is the edge length of it? The edge length of it will be D of Si half. D of Si half, D of Si half. Okay, so I'm at the case of S3. S3 includes the point P1, P2, P3. The closest pair is still P1, P2. I take the distance between them, halve it, divided by 2, and this will be the edge length. Vertically and the same horizontally. Each cell is a square.
Why we are dividing by 2?
Excellent question. Bear with me. Why did I divide by 2? Look at the points of SI. Future points, I don't make any claims of that. Pi plus 3, Pi plus 5, no claims. But look only at the points, the first I points. What could be the status of a cell? The status of a cell could be completely empty. I have infinitely many empty cells out there. Some of the cells have 1 point of SI. I'll assume that I don't have any point exactly on the boundaries, just to make the description easier. It's not an issue, but to make the description easier, I never hit exactly the point that is shared between two cells. Every point is really inside. So some cells are empty. Some cells contains 1 point. And I'll try to convince you that I don't have a cell that contains 2 points of SI. Of S by itself, sure, possibly all the points of S are inside one cell. That could be. But from SI only, a cell will contain only 1 point, at most 1 point. Why is this true? Remember, d of SI is the distance of the closest pair that I've seen so far. Let's say that the distance of the closest pair, say P1, P2, is 2 centimeters, and I picked half of this number, so it's 1 centimeter, 1 centimeter. Okay. And let's say, what are the 2 most remote points inside this cell? It will be the diagonal, and the length of this diagonal is square root of 2 centimeters, which is smaller than 2. Which means that from SI, I cannot put 2 points inside it, because then the distance between them is square root 2 is less than the closest distance that I've seen so far, which is 2. Right? So every cell is either empty or contains 1 point, but definitely not 2. Why is this useful, we'll see in a second. But at least everybody buys it. So I build the grid only when I know what is d of SI, when I know what the distance of the closest pair. Okay. Second claim. I can build, in order I time, I can build a hash table. We'll spend time in this course talking more about hashing, but at the moment, any hashing that you have seen ever will do in this application. I can build a hash table. I'll call it age for hash for the points seen so far, age of SI for the point of SI, such that, remember, in hashing I can do insert, delete, and find in constant time. You'll give me the key, and I can find in constant time, expected constant time, every point. So I can build in order of I time a hash table for y is the I, because there is only I points that are for me in this moment, such that I can do what? If I'll have a new point, Pi plus 1, I can insert it into the hash table in constant time. And given a query point Q, not necessarily a data point, giving a query point Q, I can find the cell that contains Q and tell you if there are any data points in this cell with Q or not. Q just landed here. I can ask, is there any data point of SI in this cell, based on just the X and Y coordinate of where my finger is. Q landed right here. The data structure will be able to tell me that P3 is sharing a cell with where my finger is. Okay, so first question is, how could you have only order I time when you have infinitely many cells? And the answer is simple. I'm not going to keep any cell that doesn't have a data point in it. The number of cells that have data points in them is only I. And these are the only cells that I keep, even though there is infinitely many cells. How do I decide what is the key of a point? I need to be able to, as we said, my finger has its x, y. It landed somewhere. I need to be able to access the point that lives in this cell. Same go here. Same go if there is actually a data point. How do I know that the finger on my data point, that the data point here, P1, and my finger lies in the same cell? They need to have the same key. So I need to think about a key for every point in the plane. What will be this key that I'll use in my data, in my hash function that is unique to all the points in the same cell? What I'll do is just, and assume for the moment that the size of a cell is 1 centimeter by 1 centimeter. You'll give me a point xy from the cell. I'll take the floor of x, and I'll take the floor of y. And you need to say, wait, you promised us a key, and now you're giving us 2 keys, 2 numbers. So that's fine. We'll talk about, when we'll talk about hashing, we'll see that if you have 2 numbers, then you multiply by a constant the first, plus multiply by a different constant the other, sum them up doing modulo. That's your hash function. Hash can work on 2 numbers where the keys are 2 numbers just as well as it works for 1 number. Okay, so the fact that it's not a single key but a pair of keys shouldn't disturb you. It's still 1 key. Now, why do I say that the floor operation, the floor that you see right here, does a trick for me? That's simple. Because think that of all the points that lives inside this blue cell, what's common to the all points over here? Every point in the blue cell, what its x value is between 1 and 2. What its y value is between 0 and 1 in the blue cell. So when I'm doing, I have 2 points both in the blue cell, they have the same key. The floor operation will spit out the same number because both numbers are between, if they are in the same cell, then the floor operation will spit out exactly the same integer. So that's not a problem. Cool? Every point in this cell will have the key which would be x between 2 and 3, so the floor will give you 2, and y between 1 and 2. Okay. Now, what should I do if suddenly I discovered that delta, the distance of the closest pair has changed, has decreased? 30 more seconds. Delta was decreased, and I need to, and now the size of the grid cell is delta, not 1 that we had before. That's bad news, because now the key of every point has changed. What is a key of every point? If the cell size is delta by delta, it would be from 0 all the way to delta. I need to get key of 1. From delta to 2 delta, it needs to be 2. The 2 delta to 3 delta, it needs to be 3. In short, I take x, divide by this grid size delta, take the flow, the same goes for y. However, the keys of all the points have changed when delta is changing, which will imply that I need to rehash. Rehash meaning takes all your points, takes them out of the table, compute a new hash function to each one of the points based on this delta, based on the new keys that they are getting, because delta here, the grid size has changed, and reinsert them. So if delta changes, it's bad news. Okay, yeah. We're running out of time. We'll continue Monday. Excellent, thank you. Questions so far?
Can we access to this?
Sorry?
Can we access to them, to the notes? Can we access to the notes?
Of course, I'll add it to the course website. Yeah.